Okay, so now I want to tell you about a very important concept related to groups, which is that of group actions. So remember that a homomorphism phi between a group G and a group H, so between two groups G and H, is a function satisfying that phi of a product G times H is phi of little g times phi of little h. In other words, you can first multiply in G, then apply phi, or apply phi to the individual elements and then apply phi to that. So here we have a multiplication in G. Here we have a multiplication in H. Now, group action is a way of looking at homomorphisms in the special case when H is a symmetric group. So group actions study the special case, the very important special case when H, the target, is a symmetric group. Okay, so what is the definition of a group action? So a group action is a pair Gx with G a group, X a set, together with a map psi, which goes from G times X to X, and satisfying the following axioms. So this map, it's written, it takes a pair G little x, and the image, we write it just G dot x. And like the multiplication in G, we usually even drop the dot and just write Gx. Okay, but so this is the image of the pair Gx under psi. So what should this satisfy? This should satisfy, so such that, so if I take the identity of G and multiply that on any element of X, I should get X. Nothing happens for all X in my set X. And more interestingly, if I have two elements, G and H of G, and I can do two things. I can take their product in G and then look at what is psi of the pair GH and X. That's GH dot X. And we want to ask that this is the same as the other thing I can do is I can first do H dot X, that is psi of the pair H comma X, and then I can do G dot with that. And so we want these to be equal for all G and H in G and for all X in X. As a matter of talking about group actions, when we do G dot X, we say say, action of G on X, of the element G of the group on the element or the point X of the set X. Okay? Now, what does this have to do? I was talking about homomorphisms and symmetric groups. So what does this have to do with that? Well, an action of G on the set X, when we have a pair like this Gx that is an action, we also say that G is acting on X. An action of G on X is equivalent to a homomorphism phi from G to the symmetric group on the set X. How so? If I want to define a homomorphism like this, I need to say for every G in G, I need to give a permutation phi of G. What will phi of G do to the element X? Well, it will just be the action of the element G on the element X. Okay, so we can go back and forth between this point of view of the action and the point of view of the homomorphism. Now, there is one relation satisfied by actions, one theorem, which is really fundamental in this course, and this is called the orbit stabilizer theorem. So let's state this. To state this, I need to tell you about the two concepts that appear in the name, orbit and stabilizer. So if G acts on X and X is in X, the orbit OX of X in X is the set of Gx with G in G. In other words, we look how we can move around the element little x by applying the group G. So a special case of this is we say G acts transitively on X if the action has only one orbit. In other words, we take any little x that we want and any little y in X, there is an element G in G mapping little x to little y. Okay, so this is the definition of orbit. The simplest situation is when there's only one orbit, and then we say the action is transitive. Now, what is the stabilizer? The stabilizer of an element little x in big X is, I write it stab, stab x. This is the set of elements in the group which are fixing or stabilizing little x. So the set of little g and big G such that Gx is equal to x. And you can check easily that the stabilizer of any point is a subgroup. Stab x is a subgroup of G. Okay. One last thing that I have to tell you before I can state the orbit stabilizer theorem is I have to tell you what is a map between two group actions. Okay. So this is similar to first defining what a group is, and then we have to say what is a function between groups that preserves the group structure. That's exactly what we said a homomorphism is. In this case, so a set X with an action of G is also called a G set. With this terminology, a map F from X to Y between two G sets X comma Y is a map of G sets, or G equivariant, if we have the following diagram. So I have X. I have a map from X to X given by doing G dot the element. So here I have little x goes to gx. That's this arrow. I similarly have a map from Y to Y that takes an element little y to g dot y. I have a map from X to Y, that's my F. By putting F on the two horizontal arrows, I obtain a square. And now I'm asking that this square should be commutative. In other words, if I call this map here multiplication by G, and I call this map here, well, we can also call it multiplication by G, but we should make sure to understand that here this is multiplication with respect to the first action, and here with respect to the second action. Then what we are saying here is that we can do multiplication by G here on X, compose that with F, and that should be the same as doing F and then multiplication by G, where here this is with respect to first action, and this is with respect to the second action. Okay, so now I've finished introducing all of the terms needed for the orbit stabilizer theorem. So let's actually state the theorem. So assume G acts on X, then G modulo the stabilizer of a point X is isomorphic to the orbit of X as G sets. So here we have to note that G modulo the stabilizer of X is naturally a G set where G is acting on G mod the stabilizer of X by left multiplication. So more generally, if H is a subgroup of G, then G acts on G mod H by left multiplication, by which I mean it acts by G acts on a coset XH. XH is an element of G mod H. This is equal to just GXH. Okay, and it's important to note this makes perfect sense whether or not H is a normal subgroup of G. Now, an important corollary of the theorem is here we are saying that these two sets are isomorphic as sets with G action, but in particular they are isomorphic as sets, which means that they are in bijection with one another. That is, they have the same number of elements. So a corollary is that with the same assumptions of the theorem, the order of G divided by the order of the stabilizer of X is equal to the order of the orbit of X for all X in X. Here too, this theorem is true for all X in X. And we will see later that this is particularly useful in the study of conjugation, which is one of the most important examples of group actions that we will get to.